Okay, hello everyone. My name is Nicolás Campione. I'm a lecturer here at the University of New England. And I'll be talking today a little bit about the process of weighing dinosaurs. It is a process that has over 100 years of research and may seem a bit trivial, but on the grand scheme can result in some really interesting developments about our understanding of dinosaur evolution, about their biology, and pretty much the lives of these animals. I think whenever we think of the sizes of dinosaurs, we sort of consider the really big animals. And by far the biggest animal that has been described to date is an animal known as Argentinosaurus, which was discovered in Patagonia in Argentina. And this is an animal that has been estimated to be at around 83 million grams. So that would be 83 tons. So it's a very, very heavy animal. Which sort of begs the question, how do we really get to these animals? How do scientists, from just discovering bones, are able to identify the sizes of these animals? But before we get into how we get about doing this, let's talk a little bit about why we actually care about the body sizes of dinosaurs. And if we look at animals today, they obviously have a wide range of body sizes and body masses, anything from animals like elephants to the dwarf chameleon to the bee hummingbird. There is evidently a very big range in body size. And what has come to light over the last several decades is that body size gives us a very good predictor of the ecology of these animals, how these animals were interacting with their environments. It also gives us a lot of indication about what the physiology might have been like, say their metabolism. It turns out that almost every biological property of an organism can be tied back in some form to its body size. So if we know the body size of a dinosaur, or of any extinct animal, then we have the ability to start interpreting them on a more biological rather than just descriptive and discovery basis. And so here, for instance, is an example of what we could do with an animal once we have an idea of its size. We can start to reconstruct the sizes of its muscles and start inferring, for instance, how the animal might have walked and how fast it could have run. And of course, we always have these questions. Well, how fast was T-Rex, for instance? And was the speed of a T-Rex enough to be able to take down a Triceratops or an Edmontosaurus? Well, it is through these sort of reconstructions, and it is through interpreting aspects that we can't directly see in the fossil record that we can identify these animals on a more biological level. And on top of that, the sizes of animals give us a bit of an indication of what they were maybe capable of eating. It is certainly true that a cheetah cannot eat what the lion eats, and the lion, for instance, cannot go as fast as a cheetah and cannot eat what the cheetah eats. And so body size there is a very important partitioning agent in allowing different animals to not compete with each other. So it limits that level of competition. Body size also gives us an indication of how many individuals could exist in a population. In general, small animals reproduce a lot. They make a lot of babies, and so often we'll have thousands and millions of individuals in a population, whereas larger animals often reproduce much more slowly. In the case of mammals, for instance, we can have the larger an animal, the longer the gestation period is. So that means that the longer it is actually pregnant, and having to take care of its young. And so there is generally a trade-off that the larger you are, the slower you reproduce versus the smaller you are. And this has important repercussions when we start to consider the extinction risk of animals, because in general, larger animals are at a higher extinction rate and at a higher extinction risk because of this inability to sort of recover from disasters in an efficient manner. And so there certainly has been a fair bit of work done on the body sizes of dinosaurs and trying to interpret their body sizes leading up to the end Cretaceous extinction, and whether body size may have been an important factor in their ultimate, well, the non-avian variety in the demise of the non-bird dinosaurs. So you got a gist now about sort of why we care about the sizes of dinosaurs. let's flip now to how do we know how big a dinosaur is. In living animals, it's a very trivial matter. We just have to find a scale big enough for the animal that it is, and it will give us the body mass of the animal. But in the fossil record, we don't have this ability. Fossils have undergone substantial reworking and chemical changing that no longer gives us an indication of what the bones would have weighed, so we can't use the actual weight of the fossils themselves. And so we have to find other means of doing this. And it turns out that there are two main approaches that we can take. In one case, we can make a reconstruction. We can take the skeleton of the animal, we can put on muscle, we can put on flesh, we can interpret the size of its lungs, we can make essentially a whole series of hypotheses and assumptions about what this animal may have looked like in real life. And from that, we can then try to estimate its body mass, and that is one of the procedures we will try today. The other approach is to use modern animals, modern analogs, as we like to call it, and that is to compare the bones, the limb bones specifically, but it could be any bones, to the body masses of living animals, and then come up with prediction equations that then we could then project those same limb measurements of the dinosaurs and end up with a body mass estimate. And one of the more favored ones is the use of the circumference, so that is the perimeter of the femur and the circumference, and this is generally the minimum shaft circumference because it is likely to be tied with sort of the breaking point of that limb. The thicker your limb, the more weight you can actually support. So these two approaches have been seen at odds over the last 100 years or so. But as you will see through the exercise we're doing today, they actually can work very complementary and work together to give us a better understanding of the animal that we're looking at. So we'll talk a little bit about the reconstruction approach first, because that's the one that we're going to be trying out today. This approach goes back to the early 1900s when Henry Fairfield Osborn, who was an American paleontologist, he is most notable probably for being the one to name a little-known dinosaur known as Tyrannosaurus rex. But one of the people he was working with, William K. Gregory, was a zoologist, and they were already, at the turn of the last century, looking to interpret dinosaurs on a more biological level. And so he requested that Gregory try to come up with an estimate for the animal Brontosaurus. And Gregory got the help of a paleoartist known as Charles Knight, who then created this reconstruction of Brontosaurus. And then here's the skeleton from the American Museum of Natural History. And he used an approach very similar to that we're going to use today, which is water displacement, to calculate the volume of that animal. And from there, and so on, was able to get an estimate of about 31 tons for Brontosaurus. The procedure for this is relatively straightforward. We need a reconstruction. And of course, reconstructions themselves are not trivial to create. They require quite a bit of knowledge of anatomy and assumptions of what these animals would have looked like. But nonetheless, we have a reconstruction. From that, we need some sort of technique for dunking the water, and today we'll be using a balance for dunking the specimen in water. That will give us the volume of the model. From there, we need to scale up the volume of the animal to the actual life size of the animal, the model to the life size of the animal, which will give us the volume of the dinosaur. And then we have to multiply it by some sort of assumption of the density of this animal to get the ultimate body mass. As I mentioned, the creation of a model is not a trivial one. Remember that in dinosaurs, for the most part, all we have left are the bones. But when you look around at the animals living today, almost none of them expose their bones in any great detail unless they are starving. So that means that we now have to add a fair bit of muscle and skin, organs, and all those aspects that don't generally preserve in the fossil record in order to come up with an actual reconstruction. And so often people who do reconstructions are well versed in anatomy and of living animals in order to try to sort of use that as a basis for reconstructing fossil taxa such as dinosaurs. And so quite a bit of effort has gone into kind of interpreting where certain muscles go, how big that muscle would have been, and in the end, basically creating this body envelope for a dinosaur. So the procedure that we will use today follows that pioneered by McNeill Alexander back in the 80s. And his premise, and indeed the whole premise behind dunking dinosaurs to get their body mass, is to follow Archimedes' principle, which is that any object wholly or partially immersed in a stationary fluid is buoyed up by the force equal to the weight of the fluid displaced by the object. And that's kind of a fancy way of basically saying that whatever volume of water is displaced by that submerged object, it will be equal to the volume of the actual object. And so, without further ado, let's try this out for ourselves. So here we have a replication or a reconstruction of what McNeill Alexander used back in the 80s to estimate the body mass of various different dinosaurs. And what we have is an old-fashioned scale in which it's currently in balance at some sort of equilibrium state. We have iguanodon hanging over here to the right. And then we have a set of weights hanging on the other side that have currently put this in balance. And currently we have a weight of this model at 26 grams. So the premise of what we're going to do now is actually to calculate the volume of this model is to dunk the model in water, submerge it completely, which will reduce its weight, and then the difference between the two will give us the volume of the model. So let's try that out. So now that we've filled up the water, you can see it's kind of floating in the water. So we'll remove weights from the other side to then put the balance back in a state of equilibrium.
Could you shuffle it so I can see the weight? Yeah.
That's too much? Okay, yep, the one. Amazing. So this model weighs 1 gram in water. So if we take the difference of that, which obviously is 25 grams, and so that becomes the volume of the actual model. Now, obviously, this model is not at the life size of a true iguanodon, so we have to upscale it. To that, we have to generate a scaling factor, and we'll do that by comparing the length of the femur in the model to the length of the femur in the actual specimen. So this specimen has roughly a femur length of about, we'll go with 20 millimeters. The actual dinosaur had a femur length of 1,039 millimeters, which is roughly about 1 meter long. So we can create a scaling factor of 51.9. That's our scaling factor. Now we have to cube that factor. The reason that we have to cube it is because we're comparing a length, which is a one-dimensional. Length is one-dimensional, and we want to upscale it to the actual three-dimensional animal, so we have to cube that scaling factor. And so we get a number of about 140,000. And so now we multiply that number, which is the scaling factor, to the volume of the actual of the model, which will then give us the volume of the dinosaur in real life. So here now we're getting to relatively large numbers. This number is over 3 million, but 3.5 million is the volume, so 3.5 million milliliters. Now, in order to convert a volume to a mass, we have to multiply it by some measure of density. In this case, we're going to use a density that's slightly less than water, but the reality is that most living animals, especially land animals, have densities that are very close to water. So that's generally the assumption. And when we multiply that by our body mass, we end up with a body mass that's about 3.4 million grams, so roughly about 3.4 tons. So we now have the body mass of a dinosaur estimated based off of a reconstruction. In this case, we were just using toys, but ideally, one would have actually done a much more careful job of reconstructing what this animal would have looked like. The next aspect of it is that we need to understand if that estimate was a realistic one or not. And this is a process known as validation. It's a very important one in science. We like to validate our conclusions based on multiple lines of evidence. And so we have the reconstruction approach that gave us an estimate. And so now we want to use that estimate and see if it's realistic given what we know about these dinosaurs. And for that, we can then turn to the other approach of body mass estimation, which is the use of limb scaling. So a reconstruction ends up giving us a lot of precision because we've carefully crafted the model. And so we can think of a reconstruction as basically creating a very sophisticated dart, which we can then, a lot of effort goes into making this dart or this reconstruction. And so it gives us a very precise idea of the body mass of that reconstruction. Whether it's realistic, however, then comes down to how accurate is that reconstruction. And that is where the limb scaling comes into play. Because by looking at the limb scaling, because it gives us that comparison with direct comparison with living animals, it essentially provides the dartboard for that dart. And hopefully it flies true and into the bullseye, or at least into the actual board itself. And so by combining these two methods, we get a much better grasp of that reconstruction and whether it's realistic or not, and whether we need to then reconsider some of the assumptions that went into the reconstruction, or conversely, maybe we have a very unique animal that ends up having either much thinner or much thicker limbs than one would have expected, which can then lead to further discussion about the biology of this particular individual. So in this case, we're using a proxy which is the circumference of the humerus, so that's the upper arm bone, and the circumference of the femur, which is the upper leg bone. And we get this animal, if you combine those two, we get an estimate, well, a measurement of about 828 millimeters. And then we can project that measurement and the body mass that we obtained for the dinosaur onto a plot that compares circumference to body mass in living animals. And this will give us a prediction, sort of a range, an interval where we sort of expect the body mass of an animal with these limb measurements to be. So when we do that, you'll see that the projected circumferences that we have for this animal would suggest actually a much higher body mass estimate than we got from the reconstruction. So this means that either A, this animal had much bulkier limbs than would have been expected for an animal of its size, or perhaps the model needs some reconsideration. Maybe we should go back to some of the assumptions of the soft tissue that we put onto it, some of the assumptions of body density. But nonetheless, what you can see is that by comparing these two methods, we can sort of corroborate them and try to come up with future lines of exploration. So what else can we do now that we have some body masses and we've developed, big data sets of how big these animals were? What are some of the questions that we can start to ask? Questions, things like, how did dinosaurs get so big? And so here is an evolutionary tree relationship of dinosaurs. And To that, we have projected the actual sizes of these animals in a relatively large data set of about 500 or so dinosaurs. And then we can explore how, over time and through their evolutionary history, body size has changed. And so to try to explain this a little bit more clearly, we've discovered that starting with an animal about the size of a wallaby, dinosaurs seem to have radiated in their body size very quickly. So it wasn't a steady increase in body size over time, but rather a burst of body size early on in their evolutionary history, and that actually within the first 10 to 15 million years, dinosaurs had reached almost the full extent of their body size range that they would continue to have for the rest of the Mesozoic. And so what we have are very fast rates of body size evolution early on, which we interpret to mean that dinosaurs were essentially experimenting with regions of different ecologies, different niches. They were filling in different niches very early on. Body size, remember, as we said before, is a very easy way of partitioning food resources. And so we have animals that are radiating very quickly, filling different niches. But after that, once they filled the niches, rates of body size seem to have slowed down, essentially suggesting that different dinosaurs had reached different optimal body sizes that were allowing them to fulfill their role within the trophic system. And because these had slowed down, they weren't really changing too much in size in later years. And we suggest, for instance, that this may have actually played a role when you have that meteor at the end of the Cretaceous, when you have environment changing quickly. Animals that are very optimal for a particular role, particular ecology, may be disadvantaged when that shift happens. And as a result, dinosaurs may have been stuck in these body size ruts that they couldn't get out of, and so they were less able to survive the changing environment. There was one group of dinosaurs that didn't do this, however, and that's a group we call the Maniraptorans. The Maniraptorans include things like Velociraptor, but also include all living birds. They, unlike the other groups of dinosaurs, they continue to have fast rates of body size evolution throughout their evolutionary history, throughout the end of the Mesozoic and across that boundary. And we suggest that perhaps these fast rates of body size evolution may have been played a role in their survival across the extinction. So you can see that once we have body size estimates, we can then start exploring the evolution of these animals in a much more detailed way. How about a different question? How about asking, well, why did dinosaurs get so big? This is a very tricky question and one that has been explored a lot amongst paleontologists. I'm not going to go into all of the details, but I want to run a couple of thought experiments by you. So let's explore, first of all, the ranges of body sizes that we see in dinosaurs. So here are the main groups of dinosaurs: the long-necked dinosaurs, the bird-hipped dinosaurs, or the ornithischians, and the theropods. And these bars give you the range of body sizes that we have been able to interpret from their fossils. To the theropods, we can actually add the Maniraptoran lineage. These are birds that extend all the way down to, say, something like the bee hummingbird, which is one of the smallest vertebrates in existence. And that gives us a very large range for theropods. We can then compare that to, say, mammals, specifically non-aquatic mammals. And if we add fossil mammals, we actually see that most dinosaurs actually have the same body size range or very similar body size ranges as living mammals. And most of them seem to hit a very similar limit at around that 10,000 kilogram or 10-ton mark. So even though we often think of dinosaurs as these amazingly large, much larger than animals than we see today, for the most part, we actually find that most dinosaurs actually have very similar ranges to mammals that are today, or similar to mammals if we include some of the fossil mammals. And it is really the only group that has broken that limit are the sauropods, the long-necked dinosaurs. And to try to interpret that, let's take a look at body size distributions. And so here we have a plot of how frequent, how common certain body sizes are in living mammals. We see that the vast majority of living mammals are small, generally somewhere around the 1 kilogram mark or so to the 1 kilogram to 100 gram mark, and we have much fewer of the large, very large individuals. This is a very common distribution that we see among living animals. As you said before, small animals reproduce much more quickly, and they generally have higher rates of evolution as a consequence, and therefore there often are way more small things than big things. And it turns out that this distribution is sort of, it is a balance. It is a trade-off between sort of short-term advantages of being big. And so you have, say for instance, if you are larger, you're able to compete a little bit more efficiently. You can forage more efficiently. You can move more efficiently. So there's on a very rough scale, there is a short-term benefit to being slightly larger, which is going to perpetuate things to get big, but to a point. At some point, getting large becomes risky. As we talked before, large animals often can't. You become slower at reproducing. You can't maintain viable populations for a long time, and you can get stuck into certain ecological ruts where then, when the environment changes, you are at greater extinction risk. So this distribution is the kind of depicts this balance between short-term advantages and long-term risks. And dinosaurs were likely also part of this kind of balance that we're talking about. And so as a result, this often leads to that common constraint. So probably that 10,000 kilogram limit that we're noting among dinosaurs, most dinosaurs and living mammals, probably reflects this limit of long-term constraint. Sauropods broke this, and it may be because sauropods did things a little bit differently in terms of reproduction. Sauropods have been found with very large nests, with big congregations of eggs. And what it seems like is that sauropods were reproducing potentially at a more similar rate than little animals rather than bigger animals. And so this key factor may have actually alleviated that constraint on sauropods, allowing them to get larger. And so by essence, it is quite possible that sauropods got large simply because there was nothing stopping them from getting large, not necessarily because they were being driven to get larger. So I hope I've given you a bit of an introduction to how we estimate body masses, why we care about the sizes of dinosaurs, and some of the cool research that we can do once we have these estimates.